Hi all, welcome to new lecture of Robotics and Controls. This is lecture ninth, first part of lecture ninth, and today we are going to discuss applications of Jacobian. And today we specifically discuss the application in calculating the Cartesian velocity in a manipulator, let's say. So before starting the lecture, let's recall what we studied in our last lecture. So we studied what is a Jacobian. We defined what a Jacobian is. So a Jacobian, let's say we have a function f which is from Rn to Rm, basically n inputs and m outputs, and it is a vector of functions. All right, so it's a vector of functions, and can be that vector can be given like this: f1q, f2q, fmq, where q is a vector of inputs x1, x2 to till xn. Then Jacobian is given as del f by del q, and is given as this matrix. So it's a very we also said it's a fancy way of saying what is a gradient of a vector of functions. So you calculate partial derivatives of f1 with respect to all inputs, f2, and so on and so forth till fm. So the Jacobian is an m cross n matrix where m is the number of the output of f and n is the number of inputs of f. So this was the definition of Jacobian. Now let's start with the lecture. So we'll discuss the applications of Jacobian. How is it helpful, and where we can use it. And the first we'll use we'll see three applications of it one by one in each subsequent videos. Today we are going to discuss the first application, calculating the Cartesian velocity. So let's start. So let's first of all look at theory. How are actually we going to calculate the theoretically the Cartesian velocity using the joint velocity using a Jacobian. Okay, so in previous lectures we have seen that let's say uh, PO is equal to f of q. Okay, where PO is nothing but position of a point P in frame 0 or 0, whatever. Yeah, now and Q are the joint angles. So I'll not draw the diagram. This is the forward kinematics basically. So you give the joint angles, and there is a function, and it will give you the position of the point P, where basically the end effector or whatever point we are considering. Now we know, so this is a vector of functions, this f. So let's try to write its Jacobian. So let's say let's differentiate both the sides with respect to time, let's say. Okay, so dp naught by dt is equal to d by dt of f of q. All right, so it turns out you can use a chain rule and write it as del f by del q into dq by dt. All right, so this is a chain rule, and dq by dt can be written as del f by del q dot q dot, right? And on the other hand, this is anyways dp naught by dt, which can be written as p naught. So basically this is the velocity of the point we are considering, the point in the reference point or the end effector point, whatever, right? So we can write that p naught dot equals j q dot. So j came from this is del j by del q, we saw in the last in a recall also in last lecture. So this is the first application of Jacobian. So if you know the joint velocities, you can get the end effector velocities by this. All right, to further elaborate this equation, you can write it as x dot naught. Let's say we have a 2 degree of freedom manipulator. So is equal to j times theta 1 dot, theta 2 dot, theta n dot, let's say. So basically what this is let's say we have a manipulator which has n joints but is only restricted in a 2D plane, and this is the point P, let's say. This is theta 1, theta 2, theta 3, theta 4, and each joint is moving with some angular velocity theta 1 dot, theta 2 dot, theta 3 dot, theta 4 dot. So what will be the velocity of P? That's what this relation is giving, P naught dot. And yeah, so if you know these velocities, you can use the Jacobian to find the velocity of the end effector point. So this is one of the applications. So yeah, so V velocity of point P naught is equal to J times Q dot. Cartesian, and this is the Cartesian velocity. And these are the joint angle velocities. Angular velocities. And J is the Jacobian. Okay, so this is a theory. Let's use it to write the Cartesian velocity of a 2 degree of freedom manipulator, which we wrote the forward kinematics previously. So let's see one example. Right, velocity of center of mass of the double pendulum. So double pendulum is same as 2 degree of freedom manipulator, but here we are assuming there are no joint torques. We are not applying any effort on the joints. It's not needed to know the velocities or the Cartesian velocities of any points, and it is the diagram is like this. So revolute joint, this is the first link and this is the second link. Okay, so let's say their center of mass of each link is here. Alright, so this is G1, this is G2. This is a revolute joint, and let's say this is theta 1, theta 2. These are the two angles. Okay, now let the length be C1. Let the center of mass first link be a distance C1 and from the revolute joint, and this be C2. Alright, and the overall link length be L here, because we don't need to find the velocity of this point, so we don't need the length of this. The other link, we just need the distance C2 of the second center of mass, the center of mass of the second link. Okay, so let's call these points something. Let's attach some frames, right? So let's see what is the base frame. So this is the base frame, x0, y0. All right, and the first frame attachment is here. So this is x1, y1. This is attached to the first link, and the third one is this one. This is x2 y2. So this is attached to the second link. All right. So once we know that, um, yeah, we can also write this to be O naught, O1 are coinciding, and O2 is on the other place. So what we want to do is that we know theta 1 and theta 2. You know theta 1 and theta 2. We also know theta dot and theta 1 dot and theta 2 dot. So theta 1 dot and theta 2 dot. Joint angular velocities are known. We have to find the Cartesian velocities. Of the center of masses. So V G1 naught we don't know, and V G2 naught we don't know. Alright. So we know the angular velocities and we don't know the Cartesian velocities we need to find. So in the last section we saw what the angular velocity is, right? So let's write that formula once. So Vg1 naught equals to jg1, the Jacobian of point g1, into q dot, and q dot is nothing but theta 1 dot and theta 2 dot, right? All right, this is for g1, but what can we write for g2? So Vg2 naught equals jg2 q dot. All right, now to find the velocities, what we need to find is only the Jacobian, right? Right. So because if we know the Jacobian, we just multiplied it with the q dot, and we'll get the velocities. Okay, so let's find the g1. So let's start finding jg1. All right. So jg1. Okay. Now let's first write the formula of what jg1 is. So jg1, as we saw, was given by del f g1, the forward kinematics of g1 into del q, so which is given by del g1 naught by del q. So basically g1 is the point. Let me draw the diagram. Let me copy the diagram here. All right. Right. So we want to. So jg1 is the coordinates of. This is the coordinates of this point in frame 0, 0. So let's write the. We studied homogeneous transformations, right? So let's just write the forward kinematics in that terms, and then we'll differentiate. Okay, so g1 naught is actually g11, where g11 is the coordinate of point g1 in frame 1 into h1 naught. So this is the homogeneous transformation matrix. All right, so homogeneous transformation matrix. Okay, we will get this. So this comes from the homogeneous transformation that we read, and this is the fk of that. Now what is h1 naught? Let's try to find that. So How do we find h1 naught? So let's say, so just to recall, if this is the base frame x naught, y naught, and this is the rotated frame 1, x1, y1, right? This is just rotation, there is no translation. Uh, okay, let me include translation as well so that it becomes clear. So let's say this is x1 and y1, right? And it translated by some distance, and okay. So let's say this is O1, right? So this is O1 and this is O0, right? So the way we write a homogeneous transformation matrix is, let's say this is theta. Okay. So the way we write is for this h1 naught is given by, this is for this, right? Here we'll write for that. So h1 naught can be given by cos theta minus sin theta sin theta cos theta. So this is the rotation part, right? Then there is this translation part where basically x O1 with respect to 0, y O1 with respect to 0, 1, 0, 0. So let me write this with different color. Yeah, so this is the homogeneous transformation matrix. So if your frame 1 has rotated by an angle of theta on the counterclockwise and has been displaced at a new point O1, the whose coordinates are given by xo1 and y01. So if you write them in the first frame, if you write them in frame 0, um, uh, and this is the matrix which is the homogeneous transformation matrix, right? So we can use the same concept for the double pendulum that we are considering. Okay, but please note that the angle that x1 is making has to be counterclockwise. So this is counterclockwise angle. So the angle that we need to take here is between x0 and x1 is this angle, right? So this is 270 plus theta 1 degree, right? So let's write that. So just to make it clear, this is how this is the frame x0, y0, o0, and this is the frame x1, y1, o1. So to take the angle, it has to be in the counterclockwise direction. That is by convention the positive. So we have to take this angle where this is theta 1. So and this is 270 degree, right? So whole angle is 270 degree plus theta 1, right? So yeah, so let's write that. So what is h1 naught for this case is cos 270 plus theta 1 sine 270 plus theta 1, and because their origins coincide, there is no displacement, so this will be 0, 0, 1. Then there is a minus sign, sine 270 plus theta 1 and cos 270 plus theta 1, right? 0, 0. So this is the homogeneous transformation matrix for between 1 and 0, right? Yeah. Now let's write what is G11. So this we have already written. What is this? Okay, so G11 is given by so if you look it here, G1 is along the axis itself, right? So along the x1 axis G1 lies. So if you look in the frame 1, G1 has only x coordinate, y coordinate is 0. So we can write C1 0 and 1. So this is the homogeneous form, you write 1 at the bottom. So yeah, so C1 comma 0 is the coordinate, and in homogeneous form it is represented like this. Now let's write G1 0. Let's calculate G1 0. So G1 0 will be H1 0, which is given by so cos 270 plus theta 1 will be sin theta 1, right? Minus sin 270 plus theta 1 will be cos theta 1. Minus cos theta sin 270 plus theta 1 will be minus cos theta 1, and cos theta 270 plus theta 1 will be sin theta 1, right? So this is just some trigonometric manipulation, and this is 0 0 1 0 0, right? So this is the homogeneous transformation matrix. This is H10 multiplied by C10 and 1. So this is G11, right? So let's multiply these matrices. So it will be C1 sin theta 1, and it will be minus C1 cos theta 1, and it will be 1. So this is the homogeneous coordinates of G1 in frame 0, from which we can extract only the coordinates. This is G1 0. So G1 0 is C1 sin theta 1 and minus C1 cos theta 1. Alright, now we saw that JG1 was del F G1 by del Q, and which is equal to del G1 naught by del Q. Here Q is given by theta 1, theta 2, right? So let's differentiate this and let's see what we get as a Jacobian. So JG1 equals so we can see that this is F1, this is F2, and so del F1 by del X1 is given by okay, so let's write it and just so del by del theta 1 C1 sin theta 1, and del by del theta 2 C1 cos sin theta 1. So this is basically del F1 by del F theta 1 and del F1 by just for your reference, I'll write the formula for J is equal to del F1 by del X1, del F1 by del X2, del F2 by del X1, del F2 by del X2, right? So we are writing that, and we can also write del by del theta 1 into minus C1 dot cos theta 1 and del by del theta 2 minus c1 dot sine theta 1. If you solve this, what you'll get is sine, the differentiation of sine is cos c1 cos theta 1. This will be 0 because there is no theta 2 here, right? This is c1 cos, differentiation of cos is minus sine, so this will become sine theta 1, and this will again be 0. So this is the Jacobian, right? Its rank is not full, but yeah, this is the Jacobian, so we'll write it. So jg1 equals c1 cos theta 1 0, c1 sine theta 1 and 0. So this is the Jacobian. Let's now try to find out the velocity of g1, right? So velocity of g1 is given by jg1 dot q dot, right? And q dot is c1 dot, so jg1 is cos theta 1, c1 cos theta 1 0, 0, c1 dot sine theta 1 multiplied by theta 1 dot theta 2 dot, right? So if you multiply this, you'll get, what you'll get is c1 cos theta 1 dot and c1 sine theta 1 dot, right? So this is the velocity of g1. You can see it is not dependent upon theta 2 dot at all, which is logical because it's on only link 1 and its position changes only when theta 1 changes. So this is the velocity. Yeah, so this is a 2 cross 1 vector, and you can see it is not dependent on theta 2 dot at all, right? So yeah, so this is the velocity of g1. Yeah, okay, so let's try to calculate vg2, right? So it was given by jg2 dot q dot, right? So let's try to find jg2, right? Which can be written as g2 in second frame. Let's first write the coordinates of g2 in frame 0, right? So g22 into h2 with respect to 1 and h1 is 0. So we already know this homogeneous transformation matrix, so we'll copy that from the top. We have to first find this and this, right? So let's try to write that. I'll bring the diagram from the top, copy the diagram from the top. All right, so okay, so here is the diagram. Yeah, so first and foremost, h1 naught is let's copy that from the top. H1 naught, we already know what it is. Yeah, so this is h1 naught. We'll copy this. This is h1 naught because this we simplified it here. So we'll copy this this matrix. Copy and paste. Okay, so this is the matrix h1 naught. what is H21? So let's try to write that. So how can we know H21? So um, you can see H2 has rotated counterclockwise with respect to with x1 axis. So the rotation matrix is quite normal. So cos theta 2 minus sin theta 2 sin theta 2 and cos theta 2, right? And the position is what is the position? So it is so if I draw the diagram separately, this is my first frame, frame 1, x1, y1, and this is my second frame, so x2, y2, o2, and this is theta 2, and this length is how much? This is link length L, right? So if you try to write the displacement, it is actually only can be written as L0. So this is the homogeneous transformation matrix that we can write H21, right? And now what is G22? G22 will be easy to write. So G2 in frame 2 can be written as same as previously, C2, 0 and 1. This is because G2 lies in the direction of x2 and its y2 coordinate is 0, right? So yeah, so that's how we wrote it. Okay, so I hope this this are clear. If it is not clear, just give it some time. I think it will be obvious. This is coordinates of G2 in frame 2, which lies on the x-axis of x2, right? So that is why there is no y coordinate. All right. Now let's write G20 is given by H. Let me just copy it. Copy this matrices. Select, copy, paste. Right. I'll just make it smaller. Copy, paste, make it smaller. Into this. Alright, so this is our matrix multiplication. This is H1 naught, this is H21, this is G2, right? Now let's multiply them one by one. So this will be copied as it is, and this multiplication will give you C2 cos theta 2 0 plus L, right? So because this multiplies with this, and then the second one will give you C2 sine theta 2 only, right? And then 1. So this 2 multiply and give this. Now let's give us the final result. Let's take the final result. So this is C2 cos theta 2 into sine theta 1 plus L into sine theta 1 plus C2 into cos theta 1 dot sine theta 2. Right, so this is the first element. What is the second element? So minus c2 cos theta 1 dot cos theta 2 minus L cos theta 1 plus c2 sine theta 1 plus sine theta 2, right? So, and the last one will be 1. So if you see closely, this term and this term, if they add, they form a trigonometric identity, and they actually form what they form is c2 into sine theta 1 plus theta 2 plus L sine theta 1. Alright, the second, in the second element, if you see this and this, if get added, what they will be is minus of cos theta 1 plus cos theta 2, if I'm not wrong. Okay, so minus of, so basically this was this identity was sine theta 1 plus theta 2 equals sine theta 1 dot cos theta 2 plus cos theta 1 plus dot sine theta 2, right? So this we used here. So but the second identity is what? So we want to use, so the second is cos, but actually it is negative, so negative of cos theta 1 cos theta 2 minus sine theta 1 sine theta 2, right? So this is some identity. So I think this will be minus of cos theta 1 plus theta 2. Okay, so this will it be so minus c2 dot cos theta 1 plus theta 2 minus L cos theta 1. So this identity we used here. Alright, so yeah, you can look it up. There's trigonometric identities to simplify this this expression. Okay, so this is the homogeneous coordinates of the center of mass of link 2 with respect to frame 0. Now we can extract the only the coordinates. So G20 equals the top part. Alright, so we now know G20. So G20 equals, let's copy this part, duplicate this value, right? And we know JG2 equals del G20 by del Q. Okay, so so here F1 is copy it, duplicate this, and F2 is again copy this part, is this expression. Okay, so what is del F1 by del theta 1? What is that? So if we write, that is C2 cos theta 1 plus theta 2 plus minus or plus only, I think, plus L cos theta 1, right? So this is del f1 by del theta 1. What is del f1 by del theta 2? It is C2 cos theta 1 plus theta 2, and because there is no theta 1 theta 2 here, this gives 0. Alright, so this is the first row. Now let's calculate the second. So what is del f2 by del, okay, I should write it in the way and it can have confusion. So this is del f1. Let me write the second row with different colors. So del f2 by del theta 1, what is that? So differentiation cos is sine, and there is a minus sign, and there is a minus sign there, so it will become C2 dot sine theta 1 plus theta 2. Again there is a minus sign, so it will become plus. So L sine theta 1. Alright, what is del f2 by del theta 2? It is only C2 dot sine theta 1 plus theta 2. Alright, so these are the values, so we'll just copy them. So JG2 is given as the first row is the first element, the second element, right, the third element, and the fourth element. Okay, so this is JG2. So I have calculated this. Let's now calculate it. We have calculated the Jacobian. Now let's calculate the velocity. So Vg2 theta naught, it will be given by the same matrix. So I'll just remove the distances between them slightly. This multiplied by theta 1 dot and theta 2 dot. So we'll not multiply this, but like this is the expression of the velocity of the center of mass of the second link with respect to the frame 0. So this was the application. This is Jg2 and this is q dot. Alright, so this was the first application of Jacobian, in which if you have a manipulator, you can calculate, if you know the joint angles, the rate of change of joint angles, you can know the velocity of the end effector or any point on the manipulator. If you can write it fk, you can use the Jacobian of that point to calculate the velocity of that point. Here it was a 2 degree of freedom manipulator or a double pendulum, so it was easier. You could have done it just by differentiating, just by writing the equation of the position of a point with respect to joint angles, and if you differentiate it, you would have gotten, this would have been, we could have gotten the velocities just by differentiating it. But think about a manipulator which is has 6 degree of freedom, and also there the expressions become very large. You cannot differentiate at each and every time. So if you know the Jacobian beforehand, you can calculate the velocity just by multiplying it. One last point, you can see that the Jacobian is dependent upon the joint angles, so it changes with the joint angles. So it's not a constant, it changes with the joint angle. So yeah, so for need for you to need the velocity of a point, you need at which position it is, for you to calculate Jacobian, and from that you can multiply. So keep that in mind. So Jacobian is a function of the position. So J is a function of, let's say, Q. Yeah. All right. Not F. Let's say, let's call it something else. JQ. Right. Okay. So yeah. So I'll end my lecture at this point, and in the next lecture we'll see another application of Jacobian, which is basically calculating the static forces. Okay, till then, thank you.